All right. Well, welcome everybody. Thank you for coming to my talk. I'm going to be talking about the NUMA and programming for the NUMA systems. So, well, that's what. No, that's usually not what NUMA stands for. That's usually what it stands for, although it doesn't really make that much difference. So, here is the short version of the talk first, and then the rest of the hour and a half will be the long version. The short version is 2 slides. The computers used to look like like that. We had CPUs. We had more than one for a long time. They were connected to something like front-side bus, and the front-side bus was connected to the memory. And now the computers look like that on the right. We have CPUs. Each of them is connected to the memory, and there is some kind of interconnect. And so that happened over some 20 years or so. And as a result, the programming went like this. So the bottom curve is it's actually our main threading scheduler performing tasks on a large NUMA system. The scheduler is not NUMA aware. And the number of threads actually corresponds to the number of cores. So the system has 64, maximum 64 cores. And when I rewrote that scheduler to be NUMA aware, that's the top curve in the throughput of the scheduler. So if you don't program for NUMA, you get this. Okay, so now the long version. So we're going to talk about what is NUMA, why it matters for programmers. It mostly matters for performance. Unless there are any bugs in hardware, it shouldn't matter for correctness. There are fairly straightforward consequences. There are somewhat non-intuitive and then downright weird things. I'm going to put a lot of attention on how to debug NUMA issues, because it's in general hard, but there are a few fairly easy things you can do that are very helpful. So I'm going to show the common and simple things, and if you get to the weird stuff, you're largely on your own. So let's first talk about what's NUMA stands for Non-Uniform Memory Architecture. Well, if there is a non-uniform memory architecture, what's the uniform architecture? Uniform architecture is what we had, for example, in all x86 CPUs, like Pentium. There might be one or two or more CPUs. They're connected to what's called front-side bus, and that's the interface to the memory. This is the block diagram of one of the Pentium family chips. The processor is here. That's the front-side bus. This part is actually on the motherboard, and the north bridge part of the chipset is what has the memory controller, and the memory is connected to that. So if you have multiple CPUs, they all connect to this north bridge. Now, it's actually not just that the old hardware with front-side bus has uniform memory architecture. This is Skylake, one of the latest Intel CPUs. So it has multiple CPU cores, their own caches, last level cache L3, and here is the thing they now call system agent. And it actually has an embedded memory controller. So Northbridge is on the chip. Well, Southbridge is also on the chip, but that's not important right now. What used to be Northbridge is on the chip. The memory controller is here. And that's what connects to memory. So the diagram looks like this. These are all the cores. This is the shared cache. That bottom arrow, that's the memory controller, and the memory is there. So this is still uniform memory architecture. That same processor can be in a NUMA configuration. Because the other part of that system agent is are these UPI links. So let's see how, so we saw the uniform architecture, so let's see how the non-uniform architecture looks like. That same processor, so here is your processor. This is what we saw on the previous slide, this whole thing. We now put in this one box, and it's connected to a memory by its, through the memory controller and its system agent, and it also has these interconnect links. Like this one and this one. And that's what it uses to connect to other processors. Note that each processor has its own memory controller. There is no single memory controller on the motherboard. So there is no memory controller on the motherboard, period. Which means that each processor has its own interface to the memory. However, when you program for the system, you don't see it. You have a single global address space. Yes?
It seems like each processor has its own memory as well, or have I misunderstood the diagram?
You mean the physical memory? Yeah. So each processor has its own, so there's the memory controller is right here in the CPU. It's sitting like right behind the L3 cache. So each processor has its own physical link to the memory, and yes, its own memory. So on these systems, the memory is like physically linked to the CPU. And but when you program for it, this is not like a distributed message passing system. You write an instruction, you index into the array, and the array is scattered all over this memory, and the indexing is just contiguous. But the physical memory is not symmetrically positioned with respect to the processor. So this processor works with this memory through its memory controller. This processor works with this memory through this interconnect link. So there is a non-uniformity. That's what the non-uniform comes from. Yeah?
This is just a minor clarification on the previous slide. Are the diagonal CPUs also connected with interconnects?
May or may not be. I'll show you the. Okay, so this is the Skylake. So this is like where the memory controller is built. The memory controller is built into the chip. And this says here that they have 2 or 3 interconnect links. And that's just different chips. If you have 2, you get this. Well, first of all, you may not have 4 sockets, you may only have 2. Then the question doesn't come up. If you have 4, it may or may not have a diagonal, depending on whether or not you have the 3rd link. And that's just the different chips. So if you look at the nomenclature, very popular Intel chip 6226, if it has letter R after it, it's 2 links. Without R, it's 3. So in the x86 world, this is the history of NUMA. Actually, AMD actually beat Intel to it. They introduced it first with the Hyperconnect. That was their name for that cross-CPU link. Intel introduced the same concept in Nehalem architecture first, and the name for the interconnect was QPI, Quick Path Interconnect, and now it's called UltraPath UPI. That's what UPI stands for. All of these systems now have integrated memory controllers. They replace the entire chipset, both north and south bridge. It's all on chip now. Now, the actual NUMA is older than this. I couldn't find like which one was exactly the first. It's probably one of the Honeywell systems from early 90s. This is HP was also like right there at the forefront. This is an HP system. You can actually see like these are the CPU sockets. This is the memory. And just from the structure of it, you can guess that on the motherboard there is a path from this CPU to this memory, from this CPU to this memory, and somewhere in here there is the interconnect link, whatever they did for their CPUs. These systems in general are fairly small, but they don't have to be. That's one of the early Cray systems. On the bottom. Now, it's also not true that all multi-socket systems are NUMA. This is a perfectly viable architecture for a large system. And for example, HP Superdome looks like this. Sun made very large systems that also have this architecture. There is a global interconnect. And everything is connected to it. The multiple memory banks and multiple CPUs are connected to this global interconnect. So it's symmetric with respect to the links between CPU and the memory. At least architecture, the interconnect, if the interconnect is a ring, then it's not entirely symmetric because of the travel time. But for example, like large Sun systems had a crossbar fabric, optical fabric interconnect, which was a point-to-point. It had enough bandwidth to link everybody to everybody at the same time. So in that case, it was fully symmetric. So why are we paying more attention to NUMA systems now? Like on that first curve that I've shown you for performance, like why didn't I hit that problem 10 years ago? Well, several reasons. One, systems with multiple chips became multiple CPU sockets became a lot more common and a lot cheaper. A two-socket x86 system is now kind of the mainstream system for data centers. That's like what most people buy. High-speed symmetric interconnect is expensive. It consumes a lot of power. It's very complex. Big change is the memory controllers have moved to the die. And they naturally favor NUMA because if you have memory controller on each CPU, it's hard to have uniform memory architecture if you don't have like an external memory controller that would make the memory symmetric. On the other hand, many large systems that existed that even fit those criteria avoided the issue altogether simply by not having global shared memory. Anybody here programmed for Paragon? Very large Intel system from mid-90s. It simply didn't have global addressing. You did message passing. Okay, so anybody knows what TM5 is? Thinking machines? It is slightly earlier, large systems, same thing. Multiple CPUs, each with its own memory, message passing. Now, on the other hand, now the NUMA systems are fairly mainstream. So this is a very common CPU. It's about 900 something today. And it can do, it goes typically into two-socket systems. It's designed for two-socket motherboards. And it has an on-chip memory controller, so it will be a NUMA system. All right, so let's start with performance implications. Any questions on the architecture itself? Okay. So again, this is the diagram. There may or may not be the cross-connect. It doesn't really matter. It matters from the point of view of the latency, but conceptually it makes no difference. This entire thing, the processor and the memory connected to it, is called a NUMA node. Now, looking at this, so this system has 4 NUMA nodes. Each processor runs its threads, so processes. So when we talk about a thread running, we can say it's running on this particular NUMA node. Now, of course, each processor here has multiple cores, so it's also running on one of the cores. We don't care about that for now. We just want to know which NUMA node it's running on. It's running on some NUMA node. It's possible to relocate the thread between cores. Operating system does it all the time. Those cores could belong to the same node or to different nodes. So when the OS suspends your thread and then restarts it, it could give it a different core to run. Now, each of these threads will be accessing memory. All of this memory, it looks like each CPU talks to its own memory, but actually there is a shared address space. So this memory has some addresses, this memory has like some other addresses and so on. Well, if you span your entire address space, you will hit all of them from every CPU. But each byte is in some physical memory cell, which means it's on one of these NUMA nodes. So you can have a thread running on some node, you can have its memory located in physical in memory on some NUMA node, could be the same node, could be different nodes. From this diagram, it's kind of evident that it's not symmetric. Now, it doesn't necessarily have any implications. It may be not symmetric, but may or may not be visible. But you can see that there is asymmetry, so there is a possibility for observable difference. When this thread here accesses this memory, it just hits the memory controller on chip of the CPU. If it wants to access this memory, it needs somehow to exercise the memory controller on that CPU, on the different node, on the one it's not running on. And to get there, it has to cross the interconnect. So there is at least possibility for asymmetry. So if you look at the silicon itself, accessing local memory is different from non-local memory or remote memory. And if you want to access memory from another NUMA node, you have to have some involvement of that node CPU, even though your thread is not running on it. Well, let's do some measurements. So this is just straight up memory bandwidths. We have a thread running on a CPU core, and we're measuring maximum bandwidth. This is for writing. The reading looks similar, but just I did writing. Okay. So the bandwidth depends on the size of the memory segment that you're writing. If you're writing 16 bytes, it's different from if you're writing gigabytes. So this is the size of the memory you're writing. This is the average bandwidth for that size you're going to get. This is the Intel Haswell system, two chips, 16 cores each, two NUMA nodes. Each processor has two QPI links. That's the older system. It has QPI, not UPI. This is the number of threads. So that system can run concurrently up to 32 threads before they start preempting each other. Yeah.
What does it mean to have two links, even though you only have two nodes?
It just means one is unused.
Okay.
Well, it's used. It's actually used to talk to PCIe. Okay. But we're not dealing with PCIe right now. So for the interconnect, one link is used on both of them, pointing to each other. I'm putting in just to describe fully this particular chip. Okay, so the system can run up to 32 threads without preempting. After that, they'll just start time slice. So it's after 32, obviously they'll have to divide the bandwidth simply because they're not running at the same time. So that's not interesting. Let's see what happens up to 32 thread. Now this is the bandwidth per thread. So total amount of bytes per second you can write divided by the number of threads. So the amount of bytes per second you can write on each thread. Now, okay, one thread, two, and so on. So, well, one thing you can see that it actually doesn't have enough bandwidth to feed everybody, all the cores at the same time. The memory interface isn't fast enough.
So,
yes.
So on a log scale, where would that roll off? Like if on the y-axis was log based, how would the 1, 2, 4, 8 roll off? Where does it break in?
At some point, so initially, the memory is on node 0. So all the memories right now is on node 0. Okay, initially it would be almost the same, so there's not much difference between 1 and 2, and at some point it would just strictly divide. So you double the number of threads, you would get half. That's when you're running a saturation, and there will be some transition in between.
Do you know where that point is?
It depends a lot on which CPU you're running. For this CPU, it's between 3 and 4.
Okay.
Yeah.
Does it matter on which node the thread is running for the bandwidth?
Yes. So okay. So now we need to know that, right? So, okay. So in this case, they're all running on node 0.
Oh.
So everything is now node. This is all within node, which actually means that for 32 threads, for 32 threads, I'm falling back on hyperscaling. I'm running SMT threads, so it's kind of the 32 threads. You may question, like hyperthreading. Virtual cores aren't really like full cores, in particular when it comes to their memory interface. Okay, so this may not mean anything, but up to 16, this is what you get. They're just running on the same node. So this is within node, and this is the memory bandwidth of the CPU itself. So this is the memory interface. So it can do about 18 gigabytes per second on one thread, and then it can do almost double on 2. By the time you get to 4, you're just dividing, the total maximum between threads. So after 4, you get so basically at this point, if you increase more, give it more threads, you'll just divide that maximum bandwidth between threads evenly. It's saturated, yeah.
So when we say that we have 32 threads running and there is no time slicing, but there will be all threads would be running on some operating system, and operating system will have its own thread also. So
yes, but the operating in a test like this, the operating system has nothing to do basically. So yeah,
it's not running anything.
There would be like occasional interruption, but nothing else is happening on the system. There's no I/O. Yes, operating system wakes up every now and then to
so we can ignore that.
Yeah, it's like when I monitor it, I see maybe like 2% load on one of the cores from the OS.
Okay. And the other question was, we see that as we increase the size that we are writing, the bandwidth is dropping, but that's also a factor of the large size that we are writing. So
okay, so these are caches. Like these transitions basically correspond to the cache sizes. So remember that L1, L2, L3 cache is per L1, L2 cache is per core. L3 cache is shared. And this is actually part of it, because here you have the entire L3 cache to one thread. Here you have the L3 cache divided between 16 threads. So for the same size, you only have 1/16 of the cache dedicated to your core. So you have effectively less L3 cache, which means it's hitting main memory. So like this at saturation that's the bandwidth you get from the main memory. But you effectively hit the main memory sooner. So you start feeling after this point, you start feeling the speed of the main memory, kind of average between the cache speed and the main memory, like depending on which fraction of this size fits into the cache. And here you're still at the cache size because you got all this 2 megabyte cache to yourself. So you're fine until like approximately here, where I think this is 1 megabyte cache on this one. Okay, same thing cross node. All the threads are running on node 0, all the memory is on node 1. Okay, so let's compare. For one thread, no difference. Whatever they have to feed the CPU across that entire interconnect link is fast enough to keep up with one thread. Now, this is bandwidth. So you might think it takes longer to get to the memory of the other CPU. It does, but it doesn't factor into bandwidth. Once you start streaming, it just, it probably takes a little longer to begin. At gigabytes of size of memory, it doesn't matter. So for one thread, the bandwidth of the interconnect plus whatever fraction of bandwidth of the memory controller of the other CPU you get to your own needs, fast enough. For two threads, cross node is already worse. So for two threads on the same node, it's almost the same per thread. For two threads across, it's just a little more than half of the one thread, which means the cross node link is fast enough to supply one thread at saturation, and that's almost at the limit. If it was exactly at the limit, this would be at the half. You would divide it. It's a little over half, which means the cross node link can supply barely more than one thread with memory at the speed at which the core can read memory, or write memory in this case, write memory. And after that, it goes down. So, okay, so memory bandwidth within the node is higher than between the nodes. Yes?
What does it mean? So on the far left with the small size, it looks like we're still seeing the same effect from the L1 cache and L2 cache.
Of course, because caches are per core.
So how is that measuring a cross node?
It doesn't. So when you sit in the cache,
So you're just not going cross node.
yeah. So it's an important observation that I'll highlight later. But if you can fit an L1 cache, actually for the purposes of the NUMA nodes, even if you can fit an L3 cache, because remember L3 cache is also it's shared between all cores, but it's per CPU. If you can fit an L3 cache, you don't even know that there is that other thing out there. If you don't fit an L3 cache, you start feeling this. And that will have, it kind of has the obvious implication on programming for NUMA systems, which I'll mention. Okay. Well, this is basically what it looks like. Cross-node memory bandwidths for that particular system. Yes?
I have a question on the previous slide. Is there a reason why 32 threads doesn't have the last data point?
Yes, there isn't enough physical memory on a single node to run 32 times that much. Okay, so I should have mentioned this. This is independent memory bandwidth, which means each thread is writing its own memory. It has completely nothing to do with any other thread. We'll get to dependent memory bandwidths. Okay, so this is that ratio. Cross-node, cross-node so in-node to cross-node ratio of bandwidths as a function of size for one thread. Doesn't matter. One. Same bandwidth in node and cross node. For 16 threads, that's the L1 cache. Sorry, L3 cache. L1 cache is 32K. As soon as you're out of L3 cache, you're dropping and eventually get to, this is the difference between the in-node bandwidths to memory and out-of-node bandwidths to memory when you're fully saturated. Okay, so, well, it's data. We can draw some conclusions. It actually depends a fair bit on the hardware. So this is a different hardware. This is actually a much newer chip. This is a server class Skylake. It's bigger, has more cores. It's still 2 NUMA nodes. It has newer interconnect. It has the UPI interconnect. Same thing, in-node to cross-node ratio. Even for one thread, after you're out, it has bigger L3 cache. So the transition was here on the previous slide, now it's here. It has much bigger L3 cache. But after you're out of cache, you get just over half of the bandwidths across nodes for a single thread than you get for, cross-node bandwidth is half of in-node bandwidths. Now, this is largely because in-node bandwidth is higher. This doesn't give you the absolute numbers. It's largely because in-node bandwidth on these systems is significantly higher. But that's part of like getting better performance from this chip. So you get better performance, but if you go across node, you start feeling the impact immediately. And of course, it gets worse as you go to more threads. These two pictures, this one and this one, they kind of feed into that early slide I had. Why now? Why NUMA now? If you are on this system, you can pretty much ignore NUMA, you'll be mostly okay, performance-wise. If you are on this system, you can't ignore it even on a single thread. You have significantly less bandwidth even for one thread. Yes?
Why? Because in the previous also the drop was there, so why can we ignore them?
Well, the drop is only for large number of threads. So, and the drop was like 30%. So if you have 16 threads, your bandwidth is down to 70% of peak. Like, I mean, it's not that bad, if you ignore it. If you are on this system, even on one thread, your cross-node bandwidth is half of the in-node bandwidth. So even for one thread, it's rare to have like all threads at saturation at the same time.
So why is this happening? Because over here we have better interconnect link.
But you have better interconnect link, but you have even better memory controller. Yeah.
When you set up the test bench, do you kind of task set a thread onto a specific neural node
Yes.
to get this?
Of course. And I'll talk about that. Okay, so just from these bandwidth measurements, we can already draw some conclusions for this, straightforward conclusions for the performance implications of NUMA. So just from the architecture, we know that to access the memory on the other node, that node CPU must be involved. That involvement can, obviously requires more work from the system. Depending on the system, that may or may not manifest in lost bandwidth. And in practice, for older systems, for low number of threads, it doesn't. And for high number of threads or on newer systems, it very much does. You're going to lose anywhere between around half of your memory bandwidth if your program is memory bound and you have to go across nodes. This number is actually fairly universal for like between 40 and 60%. What varies is how many threads you need to run to get there. But at saturation, it's around half of the bandwidth across nodes and within node. On the newer systems, you will experience this even for one thread. On older systems, you won't. And this general trend is that the newer systems have higher bandwidths overall, but also higher penalties for being suboptimal in the way you use it. In particular, when talking about NUMA, so being suboptimal means going across nodes. It's also important to point out that at least without data sharing, cache bandwidth is not affected. You still have L1, L2 cache per core, just like you always did. And L3 cache is per node, which means you're sharing it between cores, but you do that on non-NUMA systems as well. But there is no interaction of NUMA nodes if you're only talking to your L3 cache. Now, memory bandwidth is measured by sequential data transfers and without sharing, so it means everybody has their own memory region. Okay, but copying large chunks of memory separate for each thread is not, like I don't know, it's probably fairly popular activity in programming, but it's not all we do. Okay, now we can talk about memory latency, which is the delay, how long it takes for you to access data. Now, and there are ways to measure it, but the number of latency by itself isn't like directly relevant because it affects a lot of things you do in the program. But rather than showing you the latency, I'll show you already like the affected quantity. In this case, the affected quantity is the throughput of processing a random access data structure. So like a list whose elements are scattered randomly in memory. So you had a list, you erased a bunch of elements, you inserted a bunch of elements. After a while, these malloc locations are going to be all over the place randomly, and now you're traversing the list. Okay, so that's that same Cascade Lake 32 cores, cross-node bandwidths, in-node bandwidths. Now, first of all, one observation is it's actually lower than the sequential access. Okay, but bandwidth isn't the right word. It's throughput, and it's mainly impacted by latency because I'm touching like 8 bytes at this location and I'm jumping to the next one. So I could show you the latency. It looks kind of like this. I mean, qualitatively it looks like this. Like the numbers aren't exactly the same, and you don't really care about the latency numbers. In practice, you care about this. Like if you are impacted by latency, this it's probably because you're jumping randomly through memory. So this is what you care about. How many list nodes or how many gigabytes of memory can you process per second? Okay. So, well, first of all, random access is bad. The sequential access gave us about almost 20 gigabytes per second on this system, and random access is less than 1. Okay, but we knew that. That's the whole prefetch thing, the caches. Okay, we know that random access is bad. But it's a lot worse if you have to go cross node. So, I remember, yeah.
Sorry, what's the ratio there?
Yeah. What the real number.
Just because the bottom number
Yeah.
is so small that it's like
The ratio here is about 50. Yeah. Okay. Now, that varies a lot. I don't want to stress that this is the exact number. It varies a lot between hardware. Losing half of the memory bandwidth, plus minus 10% is fairly universal. This ratio varies a lot, and it also depends a lot on like how exactly you're measuring, what exactly random access looks like. But it's 2 digits to low hundreds. It's big. Okay, so now, if you're doing a lot of random access, of course, well, you're overall much slower. You're more likely to be memory bound. But you're also much more sensitive to the memory location with regard to NUMA nodes. Okay, so, but that's that's also fairly straightforward. But if you think that's as bad as it gets, no. So far, we have done something that very few programmers are lucky to do, which is we were accessing our memory entirely independently from each thread. Sometimes it happens, but usually you have some kind of data sharing. It's not necessarily even like true data sharing where you're updating like a shared variable. Those are bad. We need synchronization, data races, and they're slow. We know all about that. But you have some kind of large data structure, and you're updating different parts of it from different threads. You don't have any data races, but you may be writing into memory in close proximity to each other from different threads. There are no data races in this, that's fine. Okay, so let's see what happens if all threads access the same data, and again, by the same data, yes?
Is the cache line the same size across the interconnect as it would be to the main memory controller, generally?
Well, the cache line,
like for false sharing purposes.
You'll see in a moment. It's the literal answer to your question is yes, it's the same 64 bytes. But the question you really wanted to ask was when false sharing kicks in effectively, and that's a different question because it doesn't have to be tied to the cache line, and it's not entirely tied to the cache line. Okay, so accessing accessing a shared variable through data sharing requires logs or atomic access. This is slow even on one CPU. It's going to be slower across NUMA nodes. We'll actually need to talk about that, but we'll get to that later. Accessing different addresses within the same cache line is called false sharing. When you do it between different cores, it causes the cache line to bounce between caches of different cores. it has the same speed as true data sharing without any benefits. You're not actually getting any synchronization, but you're paying the full penalty in speed, so don't do it. Yes, it's worse across NUMA nodes, so really don't do it, but it was bad enough on one CPU. Okay, so let's say we're using different cache lines. Now, using different cache lines from multiple threads running on multiple cores is usually just as fast as using completely different memory, even if the cache lines are adjacent. Well, let's see what happens for the NUMA systems. So we're going to set up our test like this. Here is a cache line, 64 bytes on x86. Here is another cache line, and thread 0 is going to be hitting this cache line, and thread 1 is going to be hitting the next one, and thread 3, 4, and so on. And then thread 0 will go to the one after the last thread and keep going. So this is interleaved memory access. We're going to do sequential writes within this space. So we're going to write 64 bytes here, then 64 bytes here, then 64 bytes here, and so on. This is not random access. It's a sequential access with stride. If you did it just on one thread, it would be slightly slower than regular sequential access, but the prefetch actually recognizes the stride. So the hardware figures out that you're writing with stride and starts predicting your writes or reads at a constant stride. The hardware is really good at that. It will recognize so stride of 16, stride of 3. It will actually recognize 2 strides. If you're going every 4th and every 10th, it'll figure that out. You can see what it takes to confuse it. So on the chip, I actually just out of curiosity tried it. On this chip, it could figure out 2 mutually prime numbers, but not 3. So like 7, 11, and 13, it would completely lose its track. But 5 and 11 or 7 and 11, it figured out. We're not going to do any of that. We're going to be very straightforward. The fixed stride, and it's some kind of power of 2, depending on the number of threads. Okay. So this is within node. Everything is on node 0. For reference, this is independent. This is from the previous slide, the memory bandwidth for sequential independent writes, just so we don't have to go back to that slide. And this is the interleaved. There are some cache weirdness there that I don't know what it's from, something having to do with the prefetch. But it drops here. And this is basically what the system. So the prefetching with stride, not very effective. Sorry, the title is wrong. This is cross node. Sorry, this is cross node. Sorry, the title is wrong. This is cross node, independent and interleaved. So independent, on the Skylake system, you saw for one thread, it's losing half the bandwidth when it goes cross node compared to in node. This is interleaved. This is, of course, in order to measure interleaved memory access, you need a lot of threads. So this is running all the threads. So this is running all the threads, interleaved memory access. So this is half the threads are in node, half the threads are cross node, basically. So the memory is on node 0, but it doesn't matter which. The memory could be on node 1. It's the same. It's almost the system itself is almost completely symmetric. Node 0 and node 1 doesn't really matter. There is slight asymmetry. So the memory is on node 0, but the threads are everywhere. So it's running on every core. It's running on every core in the system. Independent access, it's independent memory regions. It's losing, compared to the cache speed, it's losing 100x, which isn't surprising. Caches are a lot faster. But this is the bandwidth you get for independent writes. Interleaved writes, half of them are in node, half of them are cross node, because you're running on every core in the system. You're down here, you lost about 50x. So this is about 0.02. You lost not quite 100x, but about 50x. when you're writing interleaved. So what happens when you write this goes back to your question. What happens when you write interleaved is there is an effect similar to the false sharing. So concurrent processing of data that is in close proximity to each other, but not on the same cache line, is going to be slower. And the fact that threads on other node are accessing it will slow down the threads on this node. And the reason is that the false sharing actually happens on the page level. The false sharing for the memory, because now we're not talking about caches, we're talking about memory. So the sharing or the false sharing of memory across interconnect happens on the page level. The entire page basically is either accessed by this CPU, or the CPU effectively locks the page momentarily and facilitates transfers to the other node. So one of the two. So having both nodes access memory in the same page, and the page on this system is 4K, has effects similar to false sharing.
So if we interleave sizes of 64 bytes instead of 64 bytes 4K, then this false sharing at the memory level will not happen.
If you make the individual sizes bigger than 4K, it will disappear.
Okay.
So so in my case, it was, so I said it's a cache line 64. If I go to, let's say, 2 cache lines, it'll become better simply because there are fewer of the chunks of these chunks in the same page, which means you're hitting the same page less often. If I go to twice as much, it'll become even better. And in practice, by the time you're like to, let's say, 2K, the odds of 2 threads, because each thread is doing its interleaved access, but it's not like they're in lockstep. They're just writing. So sometimes they'll be far apart. And yeah, you had a question?
Yeah. So if you go back to the diagram or the graph, yeah.
Oh, sorry, I went forward.
So what's the reason for the rise in bandwidth, like in the middle section?
You mean this here? I'm not sure what happens with the caches. So it's in this range. So it has a 22 megabytes shared L3 cache. So in this range, the game is the prefetch from L3 cache into L2 cache, and that's its performance. I don't really know why this chip is doing this.
Okay, but why is it higher than the independent case? Why is the independent case higher than the independent case? Like between 2048 and 32,000.
I mean, I saw it and I didn't really try to examine it because it was, the nodes aren't talking to each other. The cross node traffic is 0 up to here. So I don't know. I would have to look into the microarchitectural.
You're more often in cache, right?
You're hitting everything in cache. So
or more often in the same cache line, like.
You're probably more often in the same cache line. I don't know, the prefetcher, at this point, basically, it's how fast the prefetch can move from L3 to L2. That's the speed. For whatever reason, on this chip, this is faster. On the Haswell, it wasn't here on the Haswell, but on the Haswell also, this difference wasn't quite as large. So I'm showing just one. So I don't know why it's doing here. It requires fairly detailed analysis to figure that out. And it's also very, the other thing is, this behavior in general is very timing dependent. So your multiple threads are racing across interleaved. In my case, there was no synchronization at all. So they just go across memory and at whatever speed they want. I found that in general, this you can get like a lot of noise here depending on if you try to affect the timing of the threads. This is very timing dependent. Yeah.
So you mentioned that like when it comes to transfer memory across the nodes, it always operates on the page sizes. How does that relate, or how does like huge pages play in?
We'll see. We'll see a little later. Okay, so accessing memory in close proximity will be slower. How much slower, again, depends on hardware. On newer hardware, a lot slower. Okay, let's do something less intuitive. So, first of all, as we just saw, for for real data structures which occupy, closely, because the data structure occupies some large range of memory, but you may be accessing closely related parts of this data structure. The performance strongly depends on timing of concurrent accesses, and by concurrent I mean concurrent accesses to the same page now. So if a large fraction of accesses hits the same page often, you're going to get significant penalty, like on the order of like 20 to 100x. Now, here is something that is actually, this is where it starts to get kind of less intuitive. This is that same test. And now we're actually getting into, for the first time, I'm going to give you a hint how to very simply debug these problems. Okay. This is interleaved. So we're running we're running, the system has 64 cores scattered between NUMA nodes. We're running on all 64 cores, 64 threads. This is independent memory access, so each thread writes its own memory. This is interleaved memory access, so each thread writes 64 bytes with a stride corresponding to 64 threads. Sometimes they hit the same place, sometimes they don't. Depending on this whole thing gives you a huge mess depending on how you time the threads. So might be interesting there might be some useful conclusions you can draw from this, but it's also very hard to control timing of the threads. Timing of the threads in your actual program would basically depend on like how you jump from one place in the data structure to the other. In my case, I have like no control at all, but in reality, you would have like, I don't know, trees or lists or something like that, and you moving around would depend on the data. So maybe you're in practice more likely to visit different parts on different threads. Maybe for some reason you're visiting close parts on the same thread. It depends on the actual data structure. But this is the new one. So this is the exact same interleaved access. So the program is the same. It's 64 threads. The program is exactly the same, 64 bytes. What I did here is I locked all 64 threads to node 0. Which means I overcommitted the node, the CPU. Node 0 doesn't have 64 cores, has only 32, half the system. So I'm running 64 threads on 32 cores on node 0. And I'm getting better throughput than if I let the operating system do whatever the hell it wants.
Strange. Well, so there must be some reservation system within the hardware that's creating space for the other cores, unused previously, but now it's available to be used.
No, the other node, the CPU on the other node is completely idle at this point.
Sorry, I meant one's on the same core. There must be some
OS preempts, sure, OS preempts, but each thread gets only 50% of the time.
Understood. Sorry, I meant
the memory is on the whole system now.
The memory is always on node 0. Okay, the memory is always on node 0 or always on node 1, whatever. In this case, I put it on node 0. Doesn't matter. The memory is
the other node.
The memory is always on node 0. 64 threads running, 1 per core, writing independently. 64 threads running 1 per core, which means half are on node 0, half are on node 1, writing interleaved. 64 threads running on node 0, which means they're time slicing. Yeah.
Yeah, but when you run on all cores, then you also have the cores on node 1 having to do additional stuff for the memory access of
Yes.
node 1. And so they have to somehow drop what they're currently doing to do the memory stuff. So
It's embedded in the instruction, so the execution of the instruction basically will take longer. But the threads are not preempted. It's just the execution of the instructions take longer. Here, the OS actually time slices the threads. It can only run 32 at a time, which means at any moment of time, half of the threads are sleeping. And even with that, the fact that each thread here runs only half of real time and is totally asleep the other half, the whole thing is running faster than if I do nothing. Okay.
Is this with hyperthreading?
This system has hyperthreading enabled, yes.
Will there be a difference?
Not really. Yeah, there was a question there. No? Okay. So, in this case, running all 64 threads on the same node with 32 cores, which means each thread gets 50% of the CPU time, is faster than running one thread per core. Okay, and now we're jumping straight into how to debug NUMA issues because, I'm going to show you a very simple technique for debugging NUMA issues, and this is the technique I used to get this plot.
So, just before we move on, what's the conclusion from the previous slide then? Like, if you're node bound, if you lock
well, there is no conclusion yet. So right now we have this strange observation, and the conclusion isn't. So we don't know enough to draw the correct conclusion as far as how to program it.
Okay.
But we actually know enough to draw a correct conclusion on how to debug it.
Okay.
So to debug it, so let's say this was your program and this was all you know. Your program does interleaved access. You don't know what would have happened for non-interleaved access because that's not what you do. You don't have those data structures. I mean, you know the theoretical peak bandwidths of the system, but okay, you never get that in any real program. So you have no frame to know what percentage of my theoretical peak bandwidths could I get for this code. Well, generally you don't know. So this is what you see. As my data structure gets bigger, the performance drops. But maybe this is normal, maybe this is not normal, maybe this is the best I can do on this hardware. You don't know. What do you do? So you don't know that there is this somewhere out there because you haven't seen it yet. Well, now we need to ask ourselves. So when we run this program, we have our 64 threads accessing our data structure in some interleaved manner, and we didn't do anything at all about NUMA. Okay, if we didn't do anything about NUMA, who did? No, the OS did. What does the OS do? It manages both the threads and the memory. It assigns threads to NUMA nodes. It generally tries to minimize shifting threads between NUMA nodes, whatever policy it has. It allocates memory usually on the same node that the thread that allocated it was running. If the OS may move memory to a different NUMA node if it's consistently being accessed across nodes. That's common. Not all OSs do that, but it's pretty common. Okay, so now we're going to talk about debugging. First of all, how do you find, and everything I'm showing you is on Linux. I don't know. Yeah.
How does the OS know that you're doing these cross-socket reads?
Well, that's visible in hardware because, as I said, in order to transfer the memory to the other node, the CPU that owns the memory takes a momentary lock in hardware. That's an observable event.
So there's like a counter.
There is a counter, yeah. Okay, so everything I'm showing you is for Linux. Okay, so first of all, how to find out what you have? Like this. This tells you, okay, so this system has 120 CPUs, that's with hyperthreading, so 60 physical. 2 threads per core, 4 sockets, 4 NUMA nodes. And these are the CPUs for each NUMA node. One interesting thing is they don't have consecutive numbers. Yeah.
Is there a time where the number of sockets and the number of NUMA nodes will be different?
Not on these x86 systems, simply because they have on-chip memory controller. And I mean, in theory, you could do, you know, some kind of very complex interconnect on the motherboard, but I don't know anybody who does that. But for different hardware, it could be, yes. Okay. Here is the other one. A NUMA CTL is your main interface with the NUMA system from the command line. Same 4 nodes. CPUs for node 0, again, note that they're not consecutively numbered. And that's pretty common, don't assume that they're consecutively numbered. Node-to-node distances, it will show you this diagram. This is memory latency in some relative units, and it's not exactly like, don't draw too much into this ratio.
This is like a Cascade Lake.
This is Cascade Lake, yes. Don't draw too much into this ratio. So memory latency to your own memory is 10, memory latency to everybody else's memory is 21. It doesn't mean that it's actually exactly two times slower. It's some kind of its internal metric. You can actually ask what it really is. Intel has this memory latency checker. This will give you the actual memory latency. I'm not sure how relevant, how to translate these numbers into anything you actually observe in your program, because latency doesn't directly figure into most things you do. But, well, you can see that, first of all, it's not 2x slower. And second, there is a slight difference between diagonal and the side on this system. This kind of gives you, ballpark expectations for what you're going to get. Don't read too much into it. Now we're coming to debugging. So remember, I had this program that I was running on NUMA system. It had performance it had, and I had no idea whether that's good or bad. But I suspect that maybe there is some NUMA-related issues here. So what's the first thing I do for debugging? And this is probably like, it's the simplest message from this talk, but it's also like in practice, it's the most important. This is really, you do this, you find out that you have a problem. After that, kind of everything else follows. You can run your program bound to a particular NUMA node for the execution. So, and that's exactly what I did. I just said CPU bind 0 and run my program. That's all. And now I see that the performance of this program bound to node 0 is higher than unbound. So this tells me that I have a NUMA-related program. You can do the same thing with memory. You can also bind all memory allocations to one node, yes?
Though when I would like to allocate memory on the other node, I would get out of memory?
If you run, okay, depends what you mean by trying to allocate memory on the other node.
Yeah, when I'm bound to just one
node,
memory,
okay,
and I allocate more?
If you allocate more than this node had, you'll get out of memory.
Okay.
If you actually there is a programmatic interface where you can ask to allocate from the other node. It will override, it can override this if you want. Okay, so very simple debugging, which is, pretty much all my NUMA problems that I found and solved started with this. Run a program with all threads pinned to a single node. Run the program with all memory pinned to a single node. That turns off memory transfers between nodes. Allocation will fail if the node doesn't have enough memory. Okay, so that's that that graph that you saw. This is just like one data point, one size. So I said NUMA-CTL, bind everything to node 0, run my program. 2 gigabytes per second transfer. That's that interleaved. Okay, same thing, cross node. Threads are running on node 0, memory is on node 1. 0.67 gigabytes per second. Okay, I now know that I'm sensitive to NUMA. From this point on, I can start solving the problem, but this is always the first step. Run it completely unbound, run it bound, run it cross node, see if there is a difference. If there is, something in your program is sensitive to the NUMA issues. If there isn't, there is nothing, there is nothing to control, there is nothing to debug. Whatever you're doing doesn't care. Okay. Now, when you do this, of course, you be reasonable. Node 1 has half of, or in this case, quarter of all CPUs. So you might, bind, if you're like binding all threads to node 1 will slow down your program if it has no memory references whatsoever and simply does computing, because you've just divided, you've given it half of or quarter of all cores. Yes.
Yeah, I think I will always lose a little bit of bandwidth when I run cross node. At which ratio would you recommend that there's no problem?
Well, first of all, you may not lose any at all. If you fit an L3 cache, you're fine. At which ratio? I would say, this is kind of the upper bound on what you can get by optimizing. So if it says, for example, 90%, which means if you make it ideal, you will get back to 100. Is it worth it to you? Well, maybe it is. But that gives you kind of the upper bound on what you can get. If somehow you organize it so all your accesses are in node, you will get a 10% bump. After that, you decide. It doesn't mean that you can get the 10% bump. It may be impossible to actually organize it in this way. But this is the best case scenario. Okay, now we're getting to the weird stuff. I have a program that just does exactly what the name suggests, parallel for each. It runs parallel for each. The elements of the parallel for each are very small, and it just does a little bit of computation for each element. Okay, I'm running parallel for each. This machine has 32 cores, 32 threads, and it says almost 5 million elements per second. That's the throughput on this machine of my parallel for each. Now, the actual number, of course, depends on what I'm computing, but for this computation, this is what I get. Okay, I take the same program and I say bind it to node 0 fully. Bind CPU, bind memory. Okay, 8 million per second. Wow, I must be seriously memory bound, right? Cross node allocation is really bad because it's compute intensive. I took away half of the CPU, so the system has only 32 cores. So I took away half of the CPUs, which means I'm giving it half of the computation power, and it's still running twice as fast. So I must be seriously memory bound on this. Okay, let's see how seriously I'm memory bound. I'll run it cross node. 7.3 million, which is still better. It's a little slower, so there is some penalty for going cross node, but actually running it cross node is better than running it unrestricted on all cores of the system.
Why?
Okay, so first of all, I'm not memory bound, obviously, because if I was, there would be a huge difference here. But I am still sensitive to NUMA problems, because if I wasn't, binding it to one CPU wouldn't have made any difference. Okay, what's going on? Now, it's important to point out this, these simple benchmarks like when you do the binding to a particular node, they're very useful in revealing that you have a problem. By themselves, they're not very useful in figuring out the cause. Because, I got this, now I'm 100% certain that like something weird is going on, but I'm nowhere close to actually explaining it. To explain it, you need to go deeper, and you need to engage in hardware profiling. So there are multiple tools. There's like vTune, Linux has perf, there's a PCM. They can do some direct measurements. For example, they can measure the traffic between sockets across the UPI link. You get that number just straight up from, so that's a direct number. They can get some indirect numbers, like they can get like cache misses. They don't tell you why, but they tell you that you have them. A Linux kernel will report aggregate NUMA stats, like the number of NUMA misses while your program is running. This is actually in practice. Unfortunately, it's rarely useful because it's not that accurate. Okay, so if you have a program that runs faster under NUMA restrictions than without NUMA restrictions, you likely have some kind of NUMA-related performance issue. It's essential for your ability to debug it to be able to break down the execution time and attribute execution time to different steps in your program. Simply having timers instrumented in your program can be like a lifesaver. So just good timers for blocks of execution can be very important. After that, you have to profile, and in order to profile and be able to attribute the results to correct places, you have to simplify the problem. So you may be able to pull the offending code fragment out into a small benchmark. This is exactly what I did with the parallel for each. The parallel for each started as a step in a real program, and then it was pulled out into a benchmark of its own. Profilers give you numbers. Sometimes these numbers are helpful, sometimes they're misleading. Much more useful technique is to compare the results of the profilers with and without NUMA binding. That difference is usually much more informative than simply the numbers. Because you get like some number of some cross-node traffic or some number of cache misses. You actually don't have a frame of reference. You don't know if that, it looks larger than normal. Is it important? Should you react to that? You don't know. This is much more sensitive. You will get a lot of numbers that are the same and some numbers that are vastly different. I'll show you the examples. Also, if you have a newer CPU in-house, use it because it typically exaggerates all your NUMA-related problems. Okay, so now we run our program here, we run our program here. So without NUMA-CTL lock, with NUMA-CTL lock, this is the interleaved writing. We're going to focus on this region and run it under the profiler. Focus on this region, run it under the profiler. I'll just use vTune for this. Interleaved, CPU bound to node 0. vTune tells me I'm executing twice as many instructions per cycle when I'm bound to node 0, which is actually still low. I am heavily memory bound. Of course, I'm heavily memory bound. All I'm doing is writing into memory interleaved. I'm not here. There isn't any particular difference in cache bound and DRAM bound access issues. Okay, but vTune actually tells me directly in this case. It has a number for NUMA remote access. And if you compare the two vTune profiles for interleaved unrestricted and interleaved CPU bound, you will see this. Interleaved unrestricted, half of the traffic goes across node. Makes sense. Half of your core threads are on one node, half on the other node, and you're writing interleaved. CPU bound, everything is on one node. There is almost no cross-node traffic. Okay, so this one is easy. Okay, let's go to our parallel for each. Well, I've shown you the output for like 32 threads. this is what it looks like for different number of threads. This is kind of, it's okay, up to 8 threads, it's doing okay. And then it falls off, which incidentally is what you can fit into one NUMA node. With this is a four node system. Okay, one NUMA node without hyperthreading. So when you go to 16, you could be on still one NUMA node with hyperthreading, but the OS apparently doesn't like hyperthreading more than it doesn't like NUMA nodes, so it puts you on different NUMA nodes. Okay, I can do, I can do these NUMA CTL tests. I can lock just the CPU to node. I can lock memory to node. I can lock both to one node. So I get like these differences in my parallel for each performance. It's enough to tell me that I have a problem. It's not enough to actually tell me anything useful about where it is. Okay, now part of the problem is that we don't have enough control when we're not binding the threads. Because if you're bound all the threads to node 0, they're bound to node 0 by NUMA CTL. If you didn't bind any threads, it depends on what OS is doing. Well, you don't know what it's doing. Okay, you have to, you want something done right, you have to do it yourself. Okay, let's actually force the issue and bind every thread to its own core instead of letting the OS play its compromise between hyperthreading and different NUMA nodes, however it wants. So now each thread is on the different core and they're scattered across nodes. So one thread is on node 0, the next one is on node 1, the next one is on 2, the next one is on 3, now back to 0, like that. Okay, so that's okay, so that actually made it a lot worse. Okay, so that exaggerated the problem. Okay, let's look at the profiler. Always profile the worst, the strangest case that you see. So in our case, like 32 threads shows the biggest performance difference, relatively. So profile that case. All right, let's see what VTune gets. Okay, I'll skip the perf. Oh, okay, VTune. VTune. Okay, VTune says, so this is our parallel for each. This is the one where I bound all CPU to node 0. It doesn't matter where the memory is. As you've seen, it still runs twice as fast as unbound. Okay, more instructions per second, per cycle, still pretty low. Slightly better CPU utilization, still pretty low. Fewer front-end stalls.
What's a front-end stall?
Decoding instructions, basically, instruction scheduling. Usually caused by iCache misses, decache misses, so instructions aren't ready to be executed. Is it relevant? I don't know. Less memory bound, significantly less NUMA remote access, which is direct metric. So it's very clear, it's a very clear sign, but sign of what? I'm actually not memory bound. In fact, if I look at the code, I can see that it's mainly compute. There is very little memory use in it. And the memory bound metrics confirm it, that it's not so much DRAM bound, it's cache bound a lot, but it doesn't have enough memory to significantly hit the main memory. And yet, it's very heavily NUMA bound. And there is this front-end issue. So this is something I've got to warn you about. Hardware-assisted profiling can be severely misleading. Sometimes it not only doesn't pinpoint you the cause, it confuses you, and you actually have to go and research the matter externally. The simple debugging techniques that I've shown you is very useful, pointing out that somewhere you have a NUMA-related problem. Figuring out what it is a whole different matter. Okay. Now, one interesting thing about this test case is the entire data set actually fits into the last level cache. So there shouldn't be any NUMA traffic at all. And yet there is. A lot of it. Okay, I couldn't figure it out. I had to go to the people who designed that processor. So I had to hit my contacts at Intel. Gave them the test case. They ran it on their latest CPU in-house, and they said it's actually even worse. So that ratio that I was telling you about is getting even worse on the CPU that, well, it came out. It's the Core 10,000 something. It's out now. Okay. So they couldn't figure it out either. We had lots of discussions. Eventually, they have access to their own internal debugging tools, which see even more of what's going inside the CPU. So here is the answer. The program is latency bound. The program is latency bound in the parallel for each itself. It's not the data that it's working on. It's the scheduler, the thread scheduler. Because parallel for each basically has a task queue. And somewhere there is like the head of the task queue, which is a single shared variable. That's accessing that variable from different NUMA nodes incurs the latency penalty. Why is it worse on the new CPUs? QPI cross-node latency. 120 to 140 nanoseconds, which is only 40% of in-node latency to memory. UPI has much higher bandwidth. It's faster. It actually has higher cross-node latency, both in absolute numbers and in relative numbers. Newer systems have much higher bandwidths, but newer NUMA systems have higher cross-node latencies, very much higher in relative numbers, slightly higher even in absolute numbers. Okay, so where does that latency bite us? Here. This is your CPU, the core, L1 cache, L2 cache. This is the L3 cache. This is one per socket, the memory controller and the memory. And the QPI, UPI comes out of here. This used to be called Encore in Haswell. Now it's called System Agent. Okay, now we have two of them. Infinity, by the way, is the name on the AMD EPYC chips. Same thing, well, different protocol, but same idea. Okay, so now this entire thing is running parallel for each. And this is our shared atomic variable that controls access to the queue. Maybe it's just a spin lock. In this case, it's like the flag of the spin lock. But like this is, somewhere in the thread pool of the parallel for each, there is at least one shared atomic variable. It controls the task, handing out the tasks to the threads. Here it is, running on one CPU. We have it here on this core. We need it here on this core. To update it, it goes to the first level where the sharing, which they have access to, L3 cache. This is the first place where they can both write it. So it goes through L3 cache into the other core. You already see where that's going. Now, we have this variable. This core has it. This core wants it. It goes to the L3 cache. This core wants to look at it. Goes out to the interconnect, back into L3 cache, and here. This is your NUMA traffic. It's actually running, with this parallel for each on the Skylake, it was running at 80% saturation on the UPI link. Doing just that. Shuffling that atomic int between NUMA nodes. 180 nanoseconds each time. That's the limit on your throughput. It takes you 180 nanoseconds to figure out that you should be running a task on this core. So 180 nanoseconds per transaction. That's the upper limit on the throughput of that system, of that program. Okay, if that's true, we should be able to show it very simply. Here is a single atomic increment. Just to forget the parallel for each, just atomic increment. And yeah, here it is. Everything is on node 0. CPU is on node 0, memory is on node 1. Didn't make any difference, as expected. You know, one atomic variable, who cares? It's not even in memory most of the time. Cross node, which means threads are run, sorry, all nodes, which, not cross node memory. Cross node memory doesn't make any difference. All nodes running threads. So thread 0 is on node 1, thread 1 is on node 2, here. Okay, so for single atomic variable, you already see this impact of, that's latency, that's not bandwidth. That's the latency of how long it takes you to travel from one node to the other. So, maintaining consistent global shared space state on NUMA systems is very expensive. Okay, now we're getting to how to program. There is the NUMA API that I'm not going to, I mean, you can just read the man page for NUMA CTL, for NUMA, and it will have the list of all of these functions, or you can find them in my slide, which I'll post on Discord momentarily.
So I have a question.
Yeah.
Do the AMD chips have similar headers?
Oh, well, this is universal, yeah.
Oh, okay.
Yeah, this is universal. Okay, universal, it's a Linux thing.
Oh.
Okay, one word of caution that there are all these functions about mapping cores to nodes and nodes to cores and things like that. I don't know why, but all of these mappings are exceedingly slow. You would think that it's a lookup table. No, cache them yourself. I don't know why it is the way it is, but that's how it is. Now, obviously, you never want to throw it into the client world. So if you must use NUMA-friendly API, you have to encapsulate it. And let me show you what a NUMA-friendly program looks like. Okay. First of all, if you need to, you can bind the threads to cores. Measure it. It's actually rarely needed if you've done everything else correctly. CPU scheduler usually is good enough. So once you solve the data problem, the shared data problem, the OS scheduler is usually good enough to allocate your threads correctly without you helping it. Now the data problem. Ideally, you want your data to be within node. If it's allocated on a different node, these threads have to do a cross-node interconnect access. If this is all you do, the OS will eventually move the pages. There is nothing you can do to make this better other than not doing it. So if you're running on NUMA node, reorganize your data such that you do it, you access them in a more node-friendly way. So group, all of these accesses in one. You can be interleaved within one NUMA node as much as you want. So you have to spread the cross-node accesses. Usually one page is enough. If you're using huge pages, may not be. Now, this may require algorithm changes. Okay, let's show one more really weird case. Okay, so we've done this. We allocated our data, but we still need a shared global state. So our thread pool, parallel for each, needs shared global atomic state. There's no getting away from it. So in this case, you have to do a hierarchical global state. For example, this is a very simple thing. The parallel for each launches all the threads with all the tasks, and then somewhere it waits on the number of completed tasks. It'll give you control back when the count of completed tasks reaches, it knows how many it launched. That count is global. Hitting that count alone, every parallel for each element decrements the count. Hitting that count alone, if it travels across NUMA nodes, 180 nanoseconds per round trip. Okay, so what you do is, on node 0 there is a count. Now you have to lock these threads to node 0. You don't have to log them to cores, usually. Most of the time the OS will handle that. You have to log them to node 0. There is a count. These threads are locked to node 1. There is a count. And now we're getting into a fairly non-trivial atomic synchronization protocol, because we now have multiple counts of completed tasks and only one target count of when to stop. So your concurrent data structures are going to become more complex, because synchronization is harder, because essentially you're maintaining this hierarchy. You have to query both of these counts to figure out when to stop. Now, the good news about it is that this is read-only, and it doesn't have to bounce between pages. It just each cache has its own copy. Because read-only, they just sit in L1 caches of every CPU. They're all the same. The hardware knows that they're all the same, and there is no problem. These are being written as the task complete. These are being written to. So yeah, your synchronization, your algorithm just became quite a bit more complex, because you have to look at all of these counts, and you have to do it in a way that guarantees, looking at both isn't atomic. Looking at each one is. So you have to write the code in such a way that even though something may happen between checking this count and checking this count, you don't have a data race. This requires some creative synchronization, but this is what you have to do. So it looks kind of like this. Here are my per node counts. Here is that overall count that I'm waiting. It's going to be read-only. And here is my loop over all the nodes. This one is read-only, so I'm fine with that. These are being updated. On each node, the threads, as they complete the task, they update task counts for that node. And here I'm looping over them. And yes, this accumulation is not atomic, but that's actually fine. It doesn't cause any problems. It would cause problems if I could dynamically add more tasks after the algorithm started. But in parallel for each, that doesn't happen. You know the number of tasks up front. So for parallel for each, this is enough. Because you know the number of tasks up front, and you're never adding. Basically, the race condition here could have been that node 0 reaches 0. Okay. The node 0 reaches its value. So node 0, the task count minus node 0 reaches node 0 reaches its full task count. I'm done on node 0. Then node 1, I'm done on node 1, but while in between checking node 0 and node 1, somebody added a task to node 0. That would have been a race condition. For parallel for each, it doesn't happen because this task count is preset up front. So, if it could happen, you would have needed a different algorithm. But parallel for each in the sense is easy. So this is what basically that parallel for each looks like. There is main thread that gives everybody the tasks. Count is known. And then by pinning all the threads and their count to each node, I'm effectively running my separate thread pools. Basically, simple way to look at it is to say I have a thread pool per node. Main thread is handing out the tasks. And main thread is just waiting for the collective count of done to reach total count of tasks handed out. And that, okay, so, yeah, okay. So I've done that parallel for each, and this is what it looks like. So this was my parallel for each originally. It used to look like this. It just squished, the whole graph. This is that same parallel for each, running effectively two separate thread pools. Four on this machine has 4 NUMA nodes. So 4 separate thread pools, 1 per node. Each one has its own count, and the memory and the main thread watching all the counts and like exiting when it's done. These on the right scale is the improvement ratio, like the ratio of this to this. So at 64 threads, it's about 20. Log scale, not on the right. And this even wasn't that hard to do once we know what the problem is. But before we know what the problem is, we need to know that there is a problem. So we started with this, and maybe this is the best we can do. So, this first step of running very simple under-node bound restrictions, this first simple step was crucial to actually getting here. Because without it, I didn't even know that this is possible. Okay, now that I know that this is possible, I need to know why I'm here and not here. That took a lot of doing. And in this case required an external consult, although now you can also read about it. You can find, like on Stack Overflow on Google pages, Google search, you can find some information about this. Back then I couldn't find anything. Yeah.
You mentioned that on certain newer versions of processors, the NUMA node to NUMA node communication channels were a little bit slower. Did you ask your friends at Intel why that might be?
Price for higher bandwidth. It's the price you pay for having, basically in hardware, if you design hardware for higher bandwidths, the price is longer delay before the first transfer. And that's the trade-off they did intentionally. Okay. Want to mention one. So I told you that NUMA nodes are symmetric in every way. Not entirely in every way. And it has to do with where the hardware is connected. Network controllers. This one is connected to NUMA node 0. Well, if you're heavily network bound, does it matter? It's very hard to observe this in a simple benchmark, but for our application, like overall, 20% difference between locking the entire program to node 0 and locking the entire program to node 1 when it's running in a distributed mode. So when they're like thousands of cores on hundreds of boxes talking to each other across Ethernet, overall the program becomes 20% slower if I lock everybody to the wrong node. Now, this is the worst case scenario. Like in reality, it won't happen. But it tells me that there is some potential for optimization. I may or may not want to go after it, because in real life, it's not everybody is locked to the wrong node all the time. But like this is basically the bulk. Like I can speed up by some fraction of that if I ensure that all the threads communicating with the network are always on the right NUMA node all the time. A special case for GPUs, by the way. There is a significant difference between in-node and out-of-node transfer, but if you're memory bound on the GPU, you should be using pinned memory. And pinning memory overrides the NUMA restrictions, it's always on the right node. So if you're not using pinned memory, first look into that. If you are using pinned memory, this doesn't apply to you. So GPU is a special case. Other I/O, I don't know. I tried disk I/O. I couldn't make it bound enough to see the difference. The disks we have weren't fast enough to matter. Maybe if you have like really fast SSDs, you could observe it. I don't know.
Does every node has its own PCIe?
Yeah. Every node has its own PCIe, and every device is on a particular node. So that command that I've shown you before, this is the PCIe device ID that you can find out from LSPCI. So you plug the device ID in here, and it will tell you what node it's connected to. GPUs on a multi-GPU system are usually one per node. So like, I would have a system with 4 A100s, 4 NUMA nodes, they're one per node.
So when you have like a hard disk and M2 disk on PCIe?
It will be one of them. You will find this device here, and it will be
Yeah,
one of
but
them.
would it then matter, the node? Or is PCIe as
I
lot
don't.
slower
I
than-
I couldn't get it to matter. Maybe my disk isn't fast enough. So, in general, the bandwidth of UPI interconnect is faster than the bandwidth of your devices. So, there are good kind of initial conditions for it not being important. Okay. All right. Let's see. Are we okay for like a really weird case? Very short, really weird case. All right. So everything that I told you before doesn't apply. We have a program. It's a real program. It runs slower on the NUMA systems than on non-NUMA systems. It runs slower on the new NUMA systems than on the old NUMA systems. The profiler shows, yeah?
You mean in absolute terms, or
In absolute terms,
Okay.
yes. Even in absolute terms. Binding it to one node. So, okay, one thing that I told, so I lied to you. One thing that I told you before still applies. Binding it to one NUMA node fixes the performance problem. Which tells me that yes, it's a NUMA issue. It's very simple, it's very trivial step, but it's surprisingly useful. Running your benchmarks bound to one NUMA node on CPU, bound to one NUMA node on memory, bound to the same node on CPU and memory, cross-bound with CPU and memory, comparing the results. It's surprisingly useful. Okay, so this tells me that binding it to one NUMA node fixes the problem. The hardware profiler doesn't show anything out of the ordinary. But I do have build time reporting, and it shows me that the real time is getting longer on the new NUMA systems, and it also shows me that the real time is longer than the CPU time. And it's not. It doesn't do any I/O at all. It doesn't do any networking at all. Okay, took me like 3 weeks to figure it out. I had to get the debug kernel and profile it with kernel symbols. And I find out that, okay, the hardware profiler doesn't show anything interesting, but just the regular profiler tells me that most of the time on the newer the system and the more NUMA nodes it is, the more it gets, time is spent in the kernel. And I look at, that's where the debug symbols come in. I look at the symbols, okay, what part of the kernel it is. It's NUMA management and the TLB updates. What's TLB? Translation look-aside buffer. What's that? Virtual memory, just it's logical address space. You have these logical addresses, they don't mean anything. This is your physical memory. These are physical addresses. This correspondence is arbitrary. You have some logical addresses, they are scattered all over the physical memory. Where is this correspondence maintained? Well, that's where the translation look-aside buffer comes in. By the way, if you have two processes, they'll have their own logical space, but the same, obviously, physical memory. Okay, so who does this? Oh, the hardware level MMU, memory management unit. How does it know? In general, it just looks up the address of the physical address in the page table that is a kernel data structure. That would be very slow. Every time you have to make a kernel call to look up in the page table. There is a hardware proxy for this. This is a cache. It's very similar to associative caches we have for like L2 cache, called translation look-aside buffer. It caches frequently used entries of this page table. So MMU, first thing it does, it looks up in the cached entries. If they're in there, it actually has to go to the kernel for the full page table. Okay, fine. So far, so good. If you find the address in the TLB, you use it. If you don't find, it's called TLB miss. The kernel has to walk the page table, find the address. No big deal. There is only one page table in the kernel, of course, because there is, ultimately this is your physical, there's only one physical memory, continuous address space. There is an MMU on each processor. And there is a TLB on each processor. It would be really bad if these two were ever giving different answers to the same logical address. Who maintains this sync? This seems very similar to the cache problem. It would be really bad if the values in L3 cache were different and nobody noticed it. There is a hardware, for L3 cache, we know the answer. There is a special hardware that makes a cache line dirty, does the cache line transfer and all of that. There is none of that for TLB. There is no hardware that assists this synchronization. So who makes sure that this and this are the same? The kernel. So what happens when they get out of sync? And they do get out of sync, for example, if the kernel decides to migrate the page from one NUMA node to the other. What happens? The kernel notices that the TLBs are out of sync. The kernel now has to update the TLBs. This is called TLB shootdown. Yeah, okay. So if it gets updated, this is called TLB shootdown. I didn't come up with this, these guys did. What does the kernel do? It issues an interprocessor interrupt. It halts everything. Because you can't do anything, because any operation you can do may make MMU look up an invalid address from the TLB. It halts everything, and the control tree gets transferred to the kernel, and the kernel walks the page table and updates the TLBs on all the CPUs to the correct values. And that's why the profiler was showing that like 80% of the time was spent in the kernel in two parts of the kernel: A, the function that walks the page table, and B, the function that updates the TLB. Okay, can we prevent the TLB shootdowns? Well, we need to know why they happen. Changes in memory mapping. Yeah, every time you do an M map, there will be a TLB shootdown. Yes?
Do you know why shoot down as opposed to shut down?
You would have to read the paper. I mean, well, okay. Even the paper itself doesn't explain why. That's the term they thought. It's spelled like that. I didn't misspell it. It's spelled like that. So.
I'm sorry, we're gonna have to stop and prepare for the next session. Yeah.
Oh.
I'm very sorry. So we're gonna have to end it here.
Okay.
Okay.
I know.